Okay, our last operation from this example was a reverse of the function composition. So we did f of g of x and f of g of a specific number, so that was 4. And now we want to find g of f of 5. So there are two different ways you could go about doing this. One way would be to find g of f of x first. This is the long way, but I want to show you how to do it this way first. This is the same thing as saying find g of 2x minus 1, because if I get rid of everything around our functions, f of x is 2x minus 1. And if I plug that into my g function, that's like saying 2x minus 1 squared plus 3. Then, if my goal was to simplify this as much as possible, I would have foiling to do. So I'd do 2x minus 1 times 2x minus 1 plus 3. And then foiling here is going to give me 4x squared. I'm subtracting 2x in my inner and outer, so that's going to be minus 4x plus 1 plus 3. That's going to simplify to 4x squared minus 4x and then plus 4 if I have a plus 1 and a plus 3. So at this point, what I would want to do is plug 5 in here. So I'd have 4 times 5 squared minus 4 times 5, and then all of that is plus 4. So if you plug this into your calculator, or you can do it by hand, like 4 times 25 and so on, minus 4 times 5 plus 4, I get out 84. So that's the long way about doing function composition at a specific point if you only have to find a numerical operation. So the much easier way of going about doing this would first be to find f of 5. So if I do that, f of 5, when I plug in here, I will have 2 times 5 minus 1, which is going to give me 10 minus 1, which is 9. And so then instead of saying find g of f of 5, I can just say find g of 9 instead. So if I do that, if I plug in 9 squared plus 3 here, because I'm just replacing this x with a 9, I'll get 81 plus 3, which is 84. So I tend to think that that method is a lot simpler than this one, but they'll both get you to the right answer. And it's good to know how to do both because they're the same operation. One is just carrying along the function to the end before you plug in, and the other one is doing the numerical operations along the way. We have one more set of function operations and function composition on this next slide. Here we have f of x is x to the negative third power, and g of x is x to the 1/3 power plus 10. So once again, we get to start off with a fairly simple addition operation. It says find f plus g of 1, which is the same thing as saying find f of 1 and add it to g of 1. So if I do that, f of 1 is the same thing as saying 1 to the negative third power, and a negative exponent just means I move it to the bottom. So I'll have 1 over 1 cubed, which is still 1. So this is going to be a 1 plus. If I plug in to get g of 1, that will be 1 to the 1/3 power plus 10. 1 to the 1/3 power is still just 1. So 1 plus 10 is going to be 11. So g of 1 is 11. So this result here is just going to be 12. So a pretty easy one there. Next up, we've got a division operation. So this says find g over f of x, which is the same thing as saying take g of x and divide it by f of x. So in this case, what I want to do is write out my g of x, x to the 1/3 plus 10, and divide it by my f of x, which is negative 3. Now notice I have two terms that are over the same denominator, so what I can do is fully take a look at these two terms together, and then I can fully take a look at the 10 over x minus 3 together. That looks like Mickey Mouse ears. And so this will become x to the 1/3 over x to the minus 3, and then this is plus 10 over x to the minus 3. And then I can just see if it's possible to simplify that expression further. So if you look at the exponents on the first expression, you have a 1/3 up top and a negative 3 down below. If you divide exponents, that means you're subtracting. So what I'm doing here is taking 1/3 and subtracting negative 3. Those don't have a common denominator though, so I need to make the negative 3 negative 9/3. because if I put this over 3, I'm multiplying this guy by 3 as well, which gives me the negative 9. I have 1 minus negative 9, which means I really have 1 plus 9, which is 10/3. So these exponents are going to simplify together to become x to the 10/3 power. And then this expression just has a negative exponent, which means I need to move it up top. So I'll have 10x cubed. So that one's a little bit trickier, but it's just a matter of following your exponent rules and recognizing that you can take division step by step with each part of the numerator, dividing by the denominator, as long as there's just a single term in the denominator. Next up, we've got some more function composition. So let me try to make sure I have enough room here. And I want to find f of g of 1. Now this is kind of nice because I don't have to go through and do the full analytical function composition with x. I can just start plugging in values. So what I recommend doing first is finding g of 1, which we actually already found earlier. It was 11. So now this is saying, instead of find f of g of 1, we can just find f of 11, which means I'm going to plug 11 in to x to the negative 3rd. So I'll have 11 to the negative 3rd power, which is the same thing as 1 over 11 cubed, which is going to be a pretty big number, but we can certainly find that in our calculators. That's going to be 1 over 1,331. And that's our final answer there. Now we have one more operation here. We have g of f of x, but I think I'm a little low on space, so I'm going to get rid of this one here. And then let's try that function composition. So g of f of x is the same thing as saying find g of x to the negative 3rd power. And so if we slowly replace the x here with x to the negative 3, this will become x to the negative 3rd to the 1/3 power plus 10. And that is going to be the same thing because these are exponents, so I can multiply and distribute. That would instead be x to the negative 1st plus 10. And I can rewrite that as 1 over x plus 10. And that's my final answer there. So then let's go ahead and take a look at section 6.2. This stuff should be really familiar at this point because we've just been doing it for a while now. But what we want to do in section 6.2 is apply our exponent properties so we can work with fractional exponents. We want to simplify root expressions that have perfect cubics and quartics and quintics, but also ones that don't, and then also with working with variables there. And then we want to combine like terms with roots. So first up, we have a fractional exponent operation. We want to start by distributing this squared to every single term in here. So that's going to give me 2 squared times x. If I have a 2 and I multiply it by a 1/2, that's just going to be a 1. And then this negative 8 times 2 is going to be a negative 16. So I'm going to take this expression and multiply it by this operation over here. So I want to match the like terms. I have a 2 squared and a 2 cubed, so that's a 2 to the 5th. Then I don't have any other x terms but the x to the 1st, so I'm just going to bring that along as is. But now I have to deal with this y to the negative 16th and this y to the negative 3/4. So what we want to do there is make sure that when we add these, so negative 16 plus negative 3/4, that we're adding things that have the same denominator. So in order to make 16 something over 4, I need to multiply it by 4, which will give me negative 64. So I'll have negative 64 over 4 plus 3 over 4. So my new exponent on the y is going to become a negative 67 over 4, which is not a super pretty fraction, but that's what we have. And then let's just clean this up. The 2 to the 5th is a small enough number that I recommend simplifying it. So that's going to give you 32. X to the 1st I can just write as x. And then the negative on the y tells me to move the exponent down below. So I'll have 32x over y to the 67/4. And that's my final answer there. Then for example 2, we are simplifying a cubic root expression. So first we want to check out this 48. If you look at your perfect powers list, 48 is not a perfect cubic expression, but it is divisible by 8, which is, and 8 goes in 6 times. Then this 15 on the x is good to go because it's divisible by the 3 out here. Same thing with the 30. The 10 is the issue though, but the closest number to 10 that divides is going to be 9. So I need to break this up to z to the 9th times z to the 1st. And then I can pull out the expressions that work and leave the ones that don't inside. So cubic root of 8 is going to be 2. 6 isn't going to be able to come out, so I have to leave it underneath the root. X to the 15th is going to become x to the 5th. Y to the 30th is going to become y to the 6th. Oops, that's not right. 30 divided by 3 is 10, not 6. And then z to the 9th is going to become z cubed. But then I have this z left inside because I can't do anything else without that. So my final answer should be 2x to the 5th, y to the 10th, z to the 3rd, and then inside of the cubic root I have left over a 6z. Last part of section 6.2 asks me to combine like terms. So remember, we can combine like roots as long as they're the same index and they have the same thing inside. We can multiply any roots that are the same index. It doesn't matter what's inside. So we just want to keep track of that, knowing if we are multiplying and dividing or adding and subtracting. So here I have some square roots and some cubic roots. So I know right away I'm only going to be able to potentially combine square roots and potentially combine cubic roots. As they are right now, though, we can't do anything with them. So I need to break this up into what perfect square roots I can find, which for 50 is going to be 25 and 2. Same thing here with the 3 at root 18. I'm going to make that 3 times root 9 minus 2. Then for the cubic roots, the cubic root that's going to divide into 24 will be 8, and it goes in 3 times. And then for the cubic root of 81, the value that goes in will be 27, and 27 goes in 3 times. So now I want to simplify the perfect values. Square root of 25 is going to be 5, and I want to multiply that by the 8 out in front. So that will give me 40 times the square root of 2. Same thing here, square root of 9 is 3, and it's going to multiply with the 3 out in front. So it's going to become 9 root 2. With the cubic root, same thing, cubic root of 8 is 2, times the 2 out in front will become 4. And then there's a cubic root of 3 left inside. And then over here, cubic root of 27 is going to be 3 times 9 is going to be 27. And then I've got a cubic root of 3 left over. So now I can combine 2 sets of these terms because 40 root 2 and 9 root 2 are like terms. 4 cubic root 3 and 27 cubic root 3 are like terms. So if I add these together, I'm going to get 49 times the square root of 2. And then here I'll have minus 4 of something plus 27 of that same thing. So that's going to be plus 23 times the cubic root of 3. And that's my final answer there. Now, one thing I like to do to kind of make sure that I've simplified correctly is if I have time, I'll plug the original expression into my calculator and I'll plug my simplified expression in and just make sure the decimal values match and are equivalent. The last section is our very beginning section, section 6.1. And what we need to do in this section is convert between fractional exponents and root expressions. We need to solve equations with higher ordered exponents, and then we want to be able to evaluate root operations in our calculator. So let's do these real quick. First up, we're going to convert from a fractional exponent to a root. This has a negative in it though, so I'm going to put it down in the bottom part of my fraction. So I'll have negative 125 to the 1/3, which is the same thing as saying 1 over the cubic root of negative 125, which is the same thing as saying negative 1/5. Over here, what I want to do is add over the 2. So I'll have 3x to the 8th is 12. Divide that by 3. Divide by 3. X to the 8th is 4. So x is equal to plus or minus the 8th root of 4, or plus or minus 1.19.